welcome to this video. Believe it or not, we're actually almost done with the physics part of this unit, this kinematics unit. But before we get to the last physics topic, we do have to talk about, in order to get there, we have to talk about one math topic. What we're going to be doing today is mixing something that you already learned about, vectors, with a math topic that you probably learned in the last 2 or 3 years, trigonometry. Now, that might cause some of you to worry, because trigonometry, usually in math, you think that it's kind of hard, but the trig that we're going to be doing is extremely basic trig. You'll see what I mean in just a second. Take a look at this triangle. You're given one side of the triangle, one side length, 20, the others are x and y, we don't know them, and 2 angles. You see the 90-degree angle right here and a 34-degree angle. So this is a right triangle. How would you find A, the third side? Hopefully, you remember that in a triangle, the sum of the angles is equal to 180 degrees. So A plus 90 plus 34 has to equal 180. We could find A by therefore taking 180, subtract 90 degrees, and then subtract 34 degrees, and we get 56 degrees. A must be 56 degrees. Now, how would you find side x, the horizontal side? A lot of you would probably tell me to use the Pythagorean theorem, which is a squared plus b squared plus c squared. And while that is a useful and true theorem for right triangles, that is not going to help you here because you have 2 variables that you don't know. A squared plus b squared plus c squared is only useful if you know 2 of the side lengths already, and you only know 1. Okay? You can't solve an equation that has 2 unknowns in it. So we have to resort to trigonometry. The whole idea of trigonometry is that we've discovered that there are certain relationships between the angles in a right triangle and the lengths of the sides of that right triangle. Trigonometry is basically just a way to use those relationships to figure out a side length if you know another side length and an angle. Here's how we'd use it to find the side that's horizontal. I'm going to focus on this angle, and I don't have to, but I'm going to focus on this angle down here, the 34-degree angle, because in this class, the vast majority of the angles you see will be measured between some line and a horizontal line, which is what we have here. You don't often see angles that you have to use that are measured like this. You do on occasion, but most of the time you're going to see angles down here. So I need to find side length x. Remember that the sides of this triangle have certain names. If this is the angle I'm studying, I know that this is the hypotenuse because it's across from the right angle, right here, 90 degrees. This is the adjacent side because this is the side that's directly next to and helps form the angle. This is the opposite side, y, because that's all the way across the triangle. If I want to find x, that's the adjacent side, and I know the hypotenuse, then that means that I need to use cosine. Because, get my reference tables out, if we look on this triangle right here, if I want to find cosine of an angle, they say b over c. Here's my angle, here's b, the adjacent side, and c, the hypotenuse. I'm going to write it slightly differently. I'm going to write cosine of 34 degrees equals side x, that's the adjacent side, over 20. I don't have units for the 20, but just they could be meters, they could be whatever. It doesn't really matter at this point. In order to solve for x, you might be a little stumped. I'm going to rearrange this. I'm going to multiply both sides by 20. It's going to leave me with just x on that side. So I would have x equals 20 times the cosine of 34 degrees. That's easy enough to type into a calculator. The cosine of 34 degrees is an actual number that your calculator will spit out at you. It's a ratio. The cosine of 34 degrees tells you the ratio of if you have a 34-degree angle in your right triangle, then the cosine of 34 is the ratio of one side of the adjacent side to the hypotenuse. That's all it means. Okay? It's just a number. It helps you to solve things. You have to learn how to use your own calculator. For mine, I type in the angle first, then hit the cosine button, and then I multiply by 20. I end up with 16.58. So this x equals 16.58. I could also find y. This is the opposite side. Let's pretend I didn't find x yet. If I want to know the opposite side and I have the hypotenuse, that would be sine sine is equal to, oh, and I totally forgot. Let's talk about how you know which cosine goes with adjacent and hypotenuse, sine goes with opposite and hypotenuse. Remember this phrase, SOHCAHTOA? This is just a little mnemonic device that helps you, it's a grouping of certain letters that helps you remember which trig functions are paired with which sides. So stands for sine, goes with opposite over hypotenuse. Ca is cosine, is adjacent over hypotenuse. And toa is tangent equals opposite over adjacent. So that's how I knew that cosine was adjacent x over hypotenuse 20. And sine of the angle is equal to y, the opposite side, over 20, the hypotenuse. We're again going to rearrange this into y equals, multiply both sides by 20, 20 times the sine of 34 degrees. Type it into my calculator. I get 11.18. So interestingly, notice that the x side is longer than the y side. And you can see that on the drawing, and we also got that to reflect in the math. So that's kind of interesting. Now, okay, great math review. What the heck does this have to do with vectors? We can use this when we look at vectors because we know that any vector can be broken up into two component vectors. Maybe we don't know that, but you should be able to realize that. You can write any vector, you can draw any vector, and you can break that vector up into what we call components. And a component vector is just a vector in a very specific direction, like an easy to understand direction. The components that we use, we call them the x component, a vector that's just in the x direction, horizontal, and the y component, a vector that is just in the vertical direction. I guess they don't have to be in the horizontal and vertical direction, but a lot of times they are. What these components vectors do is they show the extent of the vector in each direction. So, for instance, if we had a 10 centimeter vector at an angle of 55 degrees from the x-axis, that vector points both in the x direction, or points both a little bit horizontally and a little bit vertically. We can break that vector up, or we can think of it as two different vectors getting added together. It's not really two different vectors getting added together, but we can think of it like that. Or it doesn't have to be two different vectors. Okay? This is the original vector, 10 centimeters. Let's say, you could picture it like an ant crawling from here to here. The x component would represent the extent of the original vector in the x direction. The y component represents the extent of the original vector in the y direction. Okay? Hopefully you can see that from this picture. We can find the x component and the y component because, by definition, the x component and y component have to be perpendicular to one another, which means there's a right angle right here, which means this is a right triangle, which means we can use trig. And if you look, this is the exact same scenario that we had up here. We knew the hypotenuse and one angle on this triangle, and we're able to find the side lengths. We know the exact same things down here. So I could find the x component. This is the x side, this is the y side, by doing this. The cosine, if I'm trying to find the x, that's the adjacent side, adjacent, and I know the hypotenuse, so I use ca, cosine adjacent hypotenuse. So cosine of 55 degrees equals x, the adjacent side, over 10 centimeters. Please make sure to put units on the 10 centimeters, and you do need this degree symbol as well. This can be rewritten as x equals 10 centimeters times the cosine of 55 degrees. And it works out to 5.74 centimeters. We can find the y component, since this is the opposite side, and we know the hypotenuse. Opposite over hypotenuse is sine, so we do sine of 55 degrees equals y over 10 centimeters, which rearranges to y equals 10 centimeters times the sine of 55 degrees. .19 centimeters. Again, notice that the y component looks bigger here, and we got a bigger number, so that's interesting. And notice that both times we found an x component, we have used cosine to find that x. In both times we found a y component, we've used sine. That is so common that it's actually in our reference table. On the back, we look at the equations. We've already talked about the first 5 equations. We have the definition of average speed, the definition of acceleration, and the three kinematics equations. Down below that is ay equals a sine theta, ax equals a cosine theta. A stands for any vector quantity. So what this means when it says ay is the y component of a vector equals the magnitude of that vector times a sine of theta. This is a theta. It's a symbol used to mean angle. It's just a 0 with a line through it, okay, horizontal line through it. So the y component of any vector equals the magnitude of the vector, the size, times the sine of the angle that the vector is at. The x component of any vector equals the magnitude of that vector times the cosine of the angle that the vector is at. I'm going to write those here because those are important. Ax equals a cosine theta, and ay equals a sine theta. You should use those equations when finding components. And again, components are not really new vectors. They're not just like magically appearing. It's a math tool that we use in order to break down the original vector. And I'll tell you why we would break down the original vector in just a little bit. But before we do that, let's practice finding x and y components. We should be able to predict which is going to be bigger, an x or a y component. Look at this. Is this vector more horizontal or is it more vertical? You should say more horizontal. And horizontal is usually the x direction, okay? Horizontal usually means the x direction and usually means we use cosine. The only time that won't be true is if you have a vector that's measured relative to a vertical line, but that's very rare. Instead of writing it like this, I'm just going to start from this equation. It's just a rearrangement of this. So you can do this if you want to, but this is the equation that's in your reference tables. That's what I'm going to start from. If we want to find the x and y components here would be the x component. Here's the y component. And then here, I suppose we could do x component, y component, x component, y component. If we want to find the x and y components, the x component is given by ax equals a cosine theta. Ax equals 7 centimeters times the cosine of the angle of 20 degrees. That's 6.58 centimeters. The y component would therefore be a sine theta, 7 centimeters times the sine of 20 degrees, 2.39 centimeters, and just like we predicted, the x component is much bigger. For this, I would predict the y component to be bigger, the vertical component. Ax equals a cosine theta, ay equals a sine theta, ax equals 14.3 centimeters times the cosine of 77 degrees, ay equals 14.3 centimeters times the sine of 77 degrees, cosine of 77 times 14.3 is 3.22 centimeters. Notice that the components have the same exact units as the original vectors, okay? And ay, the sine of 77 times 14.3 is 13.93 centimeters. This last example will be a little interesting because we're given an angle of 50 degrees. Let me just write out my equations first. The fact that we're given an angle of 50 degrees but it looks like this is a little funny because every other angle we've seen so far has been measured relative to the positive x-axis. Imagine like a little compass rose on here. Positive x-axis is over on the right-hand side. We've always measured this angle. This is telling us 50, but I'm going to make a suggestion. You really want to measure this angle here. That would be 130 degrees because we know that measuring from here all the way over is 180 minus this little 50 section, this must be 130 degrees. I'm going to tell you, you always want to measure that you want to use angles measured from the positive x-axis, and you'll see why in just a second. Ax equals 24 centimeters times the cosine of 130 degrees. We're going to type that into our calculator. Cosine of 130 degrees, we get a negative sign, multiply by 24, it's still negative. AX equals negative 15.43. I'm not going to ignore that negative. That negative is actually important. Look at this vector. The vector points to the left and up. Left, if we imagine again a little like XY chart or a compass rose, is usually the negative X direction. So the fact that this is to the left and in the negative X direction, it makes sense that our component itself should be negative. If we write 130 degrees in for our angle, the calculator will automatically tell us, the formula automatically tells us that this is a negative X component. Watch what happens if I just do 50 degrees. It tells me it's just 15.43 centimeters. That looks positive, but we know that anything to the left is usually negative, or at least we make it so it's negative. As long as you always measure from the positive x-axis for your angle, you won't have to worry about trying to think if the component should be negative or not. The calculator will tell you whether it is or not. The y component clearly isn't negative because it points up, and up is usually positive in the y direction. So this would be AY equals 24 centimeters times the sine of 130 degrees. And the y component comes out to be 18.39 centimeters. So it's just very important and something you should keep in mind that you always want to make sure that you measure any angles when using trig from the positive x-axis. It just makes your life a lot easier. If you don't, that's fine, but then you're going to have to remember that that angle was not the usual angle to measure, and you might have to throw a negative sign in front of it or take a negative sign and make something positive, and that's just too much to remember. Okay? If you follow the procedure of measuring the angle from the positive x-axis, you'll never have to deal with that. Measuring counterclockwise, I should add, from the positive x-axis. Okay, so we split a whole bunch of vectors into components, but you're probably asking yourself, why are we making such a big deal about this? Why do we have to do this? Why do we split vectors into components? And it turns out that we do this because sometimes in order to solve a problem, we only need to deal with one particular component. And we need to isolate that component and not have other parts of the vector, other components, distracting from it. An example would be this. An eastward moving boat is trying to cross a northward flowing river. So the boat's trying to go directly east. The river is flowing to the north. Due to the boat's speed and the river's flow, the boat's velocity is 5 meters per second at 53 degrees north of east. If the river is 200 meters wide, determine how much time it will take the boat to cross the river. Here's a picture of what we're talking about. Okay, here's our river. It is 200 meters wide, and I've got a boat here. The boat is moving like this. The boat's trying to go to the east, but the fact that the river is flowing north is making it so it's moving both east and north. It's moving, ultimately, at 5 meters per second at an angle of 53 degrees. Now, that's a vector, and I want to know how much time it will take the boat to cross the river. There's two different things going on here. The river is moving north, and the boat is trying to move east, so the boat ends up moving north of east because of both its own motion and the river's motion. I could take this vector and break it into components. The boat has an eastward component, and it also has a northward component to its velocity. And we can find the sizes of those components by using trig. If I want to find the x component, I know that I take the magnitude of the original vector multiplied by the cosine of the angle. That would be 5 meters per second times the cosine of 53 degrees. And within rounding, I get that this is 3 meters per second. The x component of this motion is a vector of 3 meters per second. This is the eastward component, by the way. Right there, eastward component. On the other hand, the y direction, I can find that by taking the magnitude of the vector and multiplying by the sine of the angle. And again, with rounding, this becomes approximately 4 meters per second, and this is the northward component. Now I want you to look at this and think, the boat is trying to cross the river from west to east, okay? It's trying to go to the east. What part of the boat's velocity is important for crossing the river? It's the eastward component. The northward component is never going to help it cross the river. It's just moving it downstream. The eastward component is what actually matters when trying to cross. So interestingly, even though the boat is moving 4 meters per second this way, that has nothing to do with crossing the river. So if we want to find how much time it will take the boat to cross the river, we want to find the time. We know the distance, or I guess this is a displacement. We know the displacement the boat has to go through, the horizontal displacement, the eastward displacement. We also know the speed of the boat, but since this displacement, we want to get the boat from here to here, is eastward, or I guess you could say horizontal in the x direction, we only need the speed in the x direction. Again, the speed in the y direction, the y component, that has nothing to do with crossing the river. So when we go to use our equation, v hat equals d over t, we plug in just the velocity in the x direction. We're going to multiply both sides by t. We'll get 3t equals 200. Divide both sides by 3. So 200 divided by 3. It would take the boat 66.7 seconds to cross. Now again, you might be saying, okay, well, but why do we have to use 3? Why couldn't we use 4 or 5? Well, common sense tells us that we'd get different numbers. And again, think about it. The boat was not moving 5 meters per second to cross the river. Some of that velocity was directed downstream. That doesn't get included in how much time, or in the boat's crossing of the river. That shouldn't play a role. So the fact that we used the components is really, really critical there. Okay? It's really important that you understand why we use the components and not the entire vector. And physics is full of examples where you don't need the entire magnitude of the original vector, but instead, for a certain purpose or a certain equation or a certain whatever, you only need one of those components, either the x or the y. Now, we've spent this whole time talking about breaking vectors down from an original vector into components, but that also means you can go the other way. You can take two components, a vertical and a horizontal component, and you can add them together to get the resultant vector back, okay, to get the original vector. Remember, adding vectors, we did vector addition earlier, adding vectors together means, like head to tail means put one vector, the second vector starts at the head of the first, and then so on and so forth. And when you do that, you draw a final vector from the tail of the first vector to the head of the last vector, and that's called the resultant. It is the sum of the vectors. So we've got that right here. We've got to imagine this being an x component and this being a y component. By definition, x and y are perpendicular to each other, so that's a right angle. We can figure out the magnitude of that vector and the angle it makes with the horizontal. We figure out the magnitude by using Pythagorean theorem. A squared plus b squared equals c squared. And by the way, you absolutely should be writing this equation down, and you should be using units when you plug into this equation. 15 meters squared plus 8.7 meters squared equals c squared. 15 squared is 225. 8.7 squared is 75.69 plus 225 is 300.69. Take the square root. C, which is the hypotenuse here, is equal to 17.34 meters. Okay? You can even find the angle by using another trig function. Now, the fact that we found the hypotenuse means you could use sine or cosine. But imagine you hadn't found the hypotenuse yet. You can find the angle because you know this is the opposite side, this is the adjacent side. And you know that the TOA part of SOHCAHTOA stands for tangent, opposite, and adjacent. Tangent of theta equals, in math you call them opposite over adjacent. Here, the opposite side is the y component, the adjacent side is the x component. You could even call them y over x. Tan theta equals 8.7 meters over 15 meters. Now, please don't just do 8.7 divided by 15 and say, okay, my angle is 0.58. You haven't finished the problem yet. Okay? This is an intermediate step. You don't even have to write it. We want to solve for theta. theta is the angle. Tangent of theta is just some ratio of the side lengths. It's not an answer yet, it's just a number. It's not an angle. In order to get theta, you have to do one more step, which you learned back in math class. You have to take the inverse tangent of both sides. That'll cancel out tangent over here. You'll be left with just theta. Inverse tangent looks like that, tan with a little -1, like it's an exponent. And we do that by doing second tan of 0.58. You end up with an angle of 30.11 degrees. So, based on this x component and this y component, the resultant vector has a magnitude of 17.34 meters at an angle of 30.11 degrees from the positive x-axis. Okay? You can think of it as a resultant vector. You could also think of it as the original vector that these two components were split off from. The summary of this video is right here. The rules for adding vectors using trig, because that's what we're doing. Okay, what we're doing is we're getting to, I guess we're not adding the vectors using trig yet, but we're using trig to find components and then taking those components and recreating the original vector. We can break apart a vector by using cosine to find the x component, sine to find the y component. These equations are in the reference tables. To go the other way, to take components and to create a resultant, use Pythagorean theorem, which is a squared plus b squared equals c squared, to find the magnitude, and use inverse tangent to find the angle. And again, both of these are also in the reference tables. This was a topic you first learned about in math class, but it's useful in physics, and you're going to use it throughout the year when we're dealing with vectors. I've got one more video on vectors coming up, and it's about adding vectors together. I will get to that soon. Oh, there we go. Talk to you later.